In this video, we will discuss linear transformations, which are special functions that map vectors to vectors. And in particular, to be a linear transformation, these two properties have to hold that t of u plus v, vector u plus vector v, is equal to t of u plus t of v. And the second property that has to hold is that t times au, where a is a scalar and u is a vector, is equal to a times tu. So these two things make a transformation linear. We also talk about how linear transformations can be represented by matrices, and then we look to see how that can be done. We finish by looking at null space and range as linear transformations. So in this video, we concern ourselves with the special class of functions. So now that map vectors to vectors. So for example, if V and W are subspaces in Rn, then F, if we have this, we can kind of consider this like a function that maps from V, a vector space V, to a vector space W. We're going to consider that a function whose domain is a subspace V and also another vector space W, so that we take vectors in V, map them into W, and we write this as F maps a vector V to the vector W. And then one other thing we will see, which is very important, is that linear transformations can be represented as matrices. I have this example on my summary page. I'm going to expand it a little bit here. So we can consider a function f, and it maps vectors in R3 to vectors in R2. So it looks something like this. F takes a vector in R3, in other words, that has 3 coordinates, and then it gives me a vector that has 2 coordinates. So for example, I could have f of x1, 2, 3 equal to x1 minus x2, x2 plus x3. So this will map this a vector in R3 to this vector in R2. And this definition of f, if I plug in 1, 2, 3 as my vector, then I'm going to get x1 minus x2, so that's 1 minus 2, and x2 plus x3, that's 2 plus 3, so I'm going to get negative 1, 5. So this is our example of a function that maps a vector to a vector, something from R3 to R2, but a vector to a vector nonetheless. And if we call 1, 2, 3 our vector v and our negative 1, 5 vector w, then we can notate f of v is equal to w, or f of 1, 2, 3 is equal to negative 1, 5. I haven't really gone into what it is to be a linear transformation, so I haven't shown that this function is a linear transformation, but I am going to tell you right now that it is, and I'm going to, just so that I can complete this example and this introduction, I'm going to show you that this linear transformation can be represented as a matrix. So this is our next goal for this example. And the way I'm going to find this matrix, I'm going to look at my f of x1, 2, and 3, which is equal to x1 minus x2, x2 plus x3, and I kind of wrote things so my x1s would line up and my x3s would line up, and if there's 0, I just put in extra space, just so that this matrix is easier, or these vectors is easier. I have 1 times 0, x1, plus minus 1, 1, x2, and 0, 1, x3 is equal to, right, our f of x. So if I multiply this out, I'm going to get the same thing as this. And then remember, the two ways you want to be able to look at matrix multiplication, you want to be able to look at it as a linear combination of the columns of a matrix, or you can represent these vectors as column vectors of a matrix times x. So these two are equal, and it's something you should be familiar with from the previous examples. And so what we have here is our matrix representing f. So here, if I looked at f of 1, 2, 3, I can multiply my matrix representing my transformation times 1, 2, 3, and I get negative 1, 5. So this is my first example of my overview slide. And as I said, we should back up and formally define what it is to be a linear transformation now. So let V and W be subspaces of Rn and Rm. And let T be a function from V to W. Then T goes from V to W. That's our notation, like function notation. We say T is a linear transformation for all vectors u and v in V, and all scalars A, if T of u plus V, these are vectors here, which is why they're in bold, T of u plus V is equal to T of u plus T of V, and T of AU, remember A is a scalar, is equal to ATU. And we have these two fun facts for you. First, matrix multiplication is a linear transformation, and I'll let you verify that on your own, but we will do other examples so you'll kind of get a clue of how to start this. And then also, conversely, if T is a linear transformation, then there is an n by m matrix A such that the linear transformation can be represented by AX. So T of X will be equal to A of X, much like we did over here when we said T of f of 1, 2, 3, when we plugged it in to this definition of the linear transformation, it's equal to the same thing as the matrix times the vector. And we're going to do some proofs that some functions are linear, and then we'll follow that up with functions that are not linear. But I also just wanted to give you some examples of functions that are not linear. So this x squared, the sine of x, e to the x, all of these kind of functions are not linear. Things that look like they're squared or funky are not linear. And also f of x plus 1 is not linear, which might be a little bit surprising because you don't have any x squared or x cubed terms or signs or anything else. But you will see an example like this and see why this is not linear as well. We will start by looking at functions that are linear. So here we have a function that goes from R3 to R2. So it takes a vector in R3 and it equals to this R2 vector where x1 minus x2 is, we take x1 minus x2 for the first coordinate and x2 plus x3 for the second coordinate. So this example is exactly the one we had done previously. But now we want to show it satisfies these two conditions of a linear transformation. So we're going to start with the first condition for linear transformations, which is T of u plus v is equal to T of u plus T of v. So T of u plus v, so if I have the vector u plus v, that's going to be u1 plus v1, u2 plus v2, u3 plus v3. And I plug it into my transformation. So x1, my first coordinate, so u1 plus v1, minus my second coordinate, minus u2 plus v2. And then my second coordinate plus my third coordinate, so u2 plus v2 plus u3 plus v3. And now I can rearrange algebraically, so I can group my u2s together and my v2s together. I can separate them out because these two, this is how vector addition works. So I can separate them out as a u and a v. So this is simply equal to tu plus tv. Similarly, if I want to prove my second condition for linear transformation, that is T of AU, where A is a scalar, is equal to A of TU, I start off by looking at T of AU, which is just the scalar multiple A times each coordinate in U. And then I plug this new AU vector into T. So I have my first coordinate minus my second. So that's AU1 minus AU2. And then my second coordinate plus my third. That's AU2 plus AU3. And now, just because these are all real numbers now, I can factor out my A, and then I can pull it out because this is just scalar multiplication of vectors, and this is just equal to A T of U, since this is exactly T of U. So since both of these conditions hold, F is a linear transformation. My next example, I have my function h that goes from R2 to R2. So h of x, where x, again, is in R2, so that looks like x1, x2. H of x is defined to be my first coordinate minus my second coordinate plus 1, and then 3 times my second coordinate. To look at the first condition of linear transformations, T of u plus v has to equal to T of u plus T of v. In other words, I want to show that h of u plus v is equal to h of u plus h of v. So when I look at h of u plus v, I add my vectors u and v and get u1 plus v1 as my first coordinate and u2 plus v2 as my second coordinate. Now I plug this u plus v into h. H says I want x1 minus x2 plus 1. My first coordinate minus my second coordinate plus 1. So this is my first coordinate minus my second coordinate plus 1. And then I'm going to have 3 times my second coordinate. So 3 times my second coordinate here. So again, I can group my u's together. I can group my v's together. I can separate this out. So I have u 1 minus u2 over 3u2. And I also have my v1 minus v2 over 3v2, but I have this extra 1, 0 over here. So I do have my h of u and I do have my h of v, but I have this extra 1, 0, in which case h of u plus v does not equal to h of u plus h of v because of this extra 1, 0. Therefore, this one condition, since it's been violated, is enough to show that h is not linear. But I did want to go on just to show you what it looks like to verify the second condition, which is t of au is equal to a t of u. So in terms of h, that would be h of au is equal to a hu. So a, being a scalar times u, is just equal to this, you multiply the scalar by each coordinate. So here I have au, and I'm going to plug it into h. And h, again, is my first coordinate minus my second plus 1. So my first coordinate is au1 minus my second coordinate, au2 plus 1. And then the next coordinate is 3 times my second coordinate. So that's 3 times au2. Now, if this were a linear transformation, I could manipulate this algebraically until I get this to look like a times hu. And I can do that. I can start my way by factoring out my a here. So I have a times u1 minus u2, and then I still have my plus 1. And at the bottom, I can factor out my a, and then I have my 3u2. So this portion here looks just like a times h of u, but unfortunately I still have this 1 here, so I have this extra 1, 0 added to my a times h of u. So in this case, h of au does not equal to a of hu, because I have this extra term here. And therefore, this here is also enough to show that h is not linear. I did not have to do both of these. I could have shown this does not satisfy the condition, or I could have shown the second condition is not satisfied. Each of these would have been sufficient to say h is not linear. I have one more abstract example. Let W be a subspace of Rn such that the dimension of W is equal to P. So let S equal to the vectors W1, W2 up to WP, and let's say it's orthonormal. It's an orthonormal basis for W. So we're going to define the transform from Rn to W by T of V, so V is a vector in Rn, is equal to V transpose W1 times W1, V transpose W2 times W2 plus V transpose WP, WP. We want to prove that T is a linear transformation. And remember, the thing about an orthonormal basis is all these, when you take the transpose of one vector and multiply it by any of the others, it's going to equal to 0. So like the other examples, I'm going to start by verifying this first condition that T of u plus V has to equal T of u plus T of V. So I have T of u plus V, and I plug in my u plus V into my definition of my transform, which is I take my vector and I take the transpose and I multiply it times W1, and then I take that resulting vector and multiply it times W1. So here is my vector, u plus V. I take its transpose, I multiply by W1, and then this result I multiply by W1. Now I do the same thing for W2 up to WP. So I take my vector, transpose it, multiply by W2, multiply the result by W2 up to WP. In this next step, I use the property of transpose, that when you sum two vectors and take the transpose, it's the same thing as taking the transpose of each vector and then summing. So this is what I did in this step here. For my next step, I went ahead and I multiplied my u transpose by W1 and then the result by W1, and then also my v transpose by W1 and W1, but I did group all my u's together and then all my v's. So here's my v transpose W1, W1. Then I did u transpose W2, W2, and then over here would be my next term, which I didn't write out, but would be my v W2, W2 up to the pth vector. And then what I see is that this sum here is equal to T u transpose, my grouping of u vectors, and then my grouping of v vectors is equal to T of v, which means that my T of u plus v is equal to T of u plus T of v. So this first condition for linear transforms is satisfied. The verification that T of AU is equal to A at TU is similar and also can be verified. And then you will, by verifying both of these conditions, you can conclude that T is linear. For our next example, we're going to let W be the subspace of R3 containing the vectors of the form x1, x2, 0. So you can see that W is in the xy plane since Z is always equal to 0. And the vectors E1, which is 1, 0, 0, and E2, 0, 1, 0, is a basis for W. We're going to consider a linear transformation T from R3 to R2. So from this space, R3, down to R2. And as you might guess, maybe we're just going to look at it in the xy plane. So our transform, in particular, is going to take a vector x and then multiply that vector x transpose times E1, and then the result times E1. And then we do the same for E2. So we take the transpose of the vector x, multiply it by E2, and then multiply the result by E2. Writing this out as T of x1, x2, x3, so I take x transpose multiplied by 1, 0, 0, and then multiply this result by 1, 0, 0. Then I take my vector x transpose multiplied by 0, 1, 0, and multiply this result by 0, 1, 0. And what I get when I multiply this E1 basically picks out the first component of my vector x. So I'm going to have x1 times 1, 0, 0. E2, essentially, its effect is to pick out the second component of my vector, right? Because it zeroes out the first component, picks out the second component, and then zeroes out the third component. So what I'm left with is x2 times my 0, 1, 0, which then, when I multiply and add this out, I get x1, x2, and 0. So what I get here is T is equivalent to picking out the first and the second components, and it's the same. So basically what I've written for W is the transpose definition, kind of a formula for the transpose. And T is called the orthogonal projection of V onto W. So it's this vector, and we're seeing what it looks like on W, on the subspace W. In other words, we're taking this three-dimensional vector and we're looking at sort of the shadow it would cast on the xy plane when z is equal to 0, and this is the vector we would get. Our next example, let W be a subspace of Rn and let A be a scalar. We're going to define our transpose to go from W to W by, you take your vector W and you multiply it by the scalar. We want to demonstrate that T is a linear transformation. So I start by verifying this first condition for linear transformations, that T of U plus V is equal to T of U plus T of V, so this line here. So I plug in my U plus V into my transformation, so I need to multiply by my scalar A. By distributive property of scalar multiplication, I can then algebraically, this is equal to A times U plus A times V, which is T of U plus T of V. So I have proven this first condition. For my second condition, now I need to have T of a scalar times U plus is equal to the scalar times T of U. Since I already have A here as a scalar, I put in this extra scalar here for this property as alpha. So I want to prove that T of alpha U is equal to alpha T of U. So looking at alpha U, I'll plug that into my definition and I'll get A times alpha U. So both A and alpha are scalars. So because they're both scalars, I can switch their order, and then I'll have alpha AU, which is equal to alpha T of U. So I have proved this second condition here of linear transformations. Both of them hold, so I have proven, or I've shown, that T is linear. My next example, let W be a subspace of Rn and let 0 be the 0 vector in Rn. We're going to define our transformation to go from W to Rm by T of W is equal to the 0 vector. We want to show that T is linear. It's the same two properties that we're showing hold. So we look at U plus V. We plug in our U plus V vector into T, and we get the 0 vector. But the 0 vector is just equal to the 0 vector plus the 0 vector, which is equal to T of U plus T of V. So the first condition holds. The second one, we plug in our scalar times U, into our transformation t, and we get 0. But that's just equal to a times the 0 vector, a being a scalar, which is equal to a times t of u. So the second condition also holds, and we've shown that t is linear. So we've gone through many examples of linear transformations, and now the next point that we want to see is that linear transformations can be represented by a matrix. And the fact that we use is that t of a scalar a times u, a vector u, plus a scalar b times a vector v is equal to, now breaking this up because it's a linear transformation, t of au plus t of bv, which is equal to a t of u plus b t of v. So we'll see how we are going to use this fact here to find the matrix of a linear transformation. And I move this information up so I have more space. We are going to use this example to motivate how we are going to find the matrix of a transformation. So let W be a subspace of R3 defined by the vectors x such that x2, the second and third coordinates are real numbers, and the first coordinate of our vector x is equal to x2 plus 2x3. So this is the form of our vectors in W. Then we also know that W1 and W2 is a basis for W, where W1 is equal to 1, 1, 0, and W2 is equal to 2, 0, 1. In our video about basis, we had many examples of how we would find a basis for this subspace W, but I have kind of the notes here just as a reminder. So W is defined to be x2 and x3 are real numbers. x1 is equal to x2 plus 2x3. So we can rewrite this as a vector that only has x2 plus a vector that only has x3. So that would be x2 is in the first coordinate, x2 is in the second coordinate, but there's no x2 terms in the third coordinate, so we put 0. There's 2x3 in the first coordinate, no x3 terms in the second coordinate, so we put 0. And then there's 1x3 in the third coordinate. And then the last thing we do is we pull out the x2 and x3, and we're left with 1, 1, 0, and 2, 0, 1. So these two vectors, 1, 1, 0, and 2, 0, 1, form our basis for W, because any vector in W can be written as a linear combination of 1, 1, 0, and 2, 0, 1. Now that we have our basis, we want to suppose that we have a transform T, and we know how T operates or what it does to our basis vector. In particular, TW1 is equal to 1, 1, and TW2 is equal to 1, negative 1. And what I have here is this note that if you know how T transforms a basis, then you can determine how to transform any vector in the space. So here is the last part of this problem. The actual problem statement is, suppose W, that's any vector in our space, is equal to negative 1, 3, 2, and you can check that this vector W conforms to our specifications of what W looks like. We want to show that W is in our space W by expressing W as a linear combination of W1 and W2. And then finally, we're going to use this information to determine what our matrix for T looks like. So here we have how we determine W, negative 1, 3, 2, as a linear combination of our two basis vector 1, 1, 0 and 2, 0, 1. And what we do is we solve the augmented matrix, the 1, 1, 0, 2, 0, 1, and negative 1, 3, 2. We do the row operations, and then you can see we get x2 is equal to negative 2, and then negative x1 is equal to 1 plus 2x2, so plugging in the negative 2 here for x2, we get that x1 is equal to 3. So here I've written my negative 1, 3, 2, negative 2 as a linear combination of my two basis vectors. I have x1 is equal to 3 times my first basis vector, 1, 1, 0. x2 is equal to negative 2 times my second basis vector. So the next part of our problem is to determine the matrix for T. And the first thing just to note, again, T hasn't been given to us in a straightforward definition. All we know about T is how it operates on the basis vectors U1 and W1 and W2. which is this part here, we know how T transforms the bases. So we're going to use the fact that T is linear and that we can write any vector W in our space as a linear combination of the bases vectors. So in terms of our particular example, when we want to look at how T transforms the vector -1, 3, 2, we're going to use the fact that we can write our vector -1, 3, 2 as a linear combination of our bases vector, and that's what we did in the first part of this problem. And here we have our vector 1, 3, -2 as a linear combination of our two bases vectors. Since T is linear, T of 3, 1, 1, 0 minus 2 times 2, 0, 1 is equal to 3T, 1, 1, 0 minus 2T, 2, 0, 1. And again, this is also this fact up here that we're using. So I'll just put a little arrow. And working this out, this is just 3 times the transformation of our first bases vector is defined somewhere here as 1, 1. The minus 2 times the transformation of our second basis vector, which is here, 1, -1. And then you multiply 3, 1, 1, and you get 3, 3. You multiply -2, 1, -1, you get -2, 2. Add them together, and you get your final solution, 1, 5. And the big takeaway is if you know how T transforms a basis, then you can determine how T transforms any vector in the space. Essentially because 1, you can rewrite your vector as a linear combination of the bases, and then 2, if it's a linear transformation, you can use this property here then to finally calculate the transformation of T on any vector W. This next example will show if we know how T operates on the standard basis, it makes things even easier. So let's let T be a transformation from R3 to R2. It's going to be a linear transformation such that T transforms E1 into 1, 2, transforms E2 into -1, 1, and E3 into 2, 3. We want to give a formula for the matrix T of X, where X is the three-dimensional vector. And again, the first thing that we use is the fact that our vector X can be written as a linear combination of our bases. And then, after that, we plug in our linear combination into T. So here's X as a linear combination of our bases. We plug that into T, and what we get is, again, because it's a linear combination, we can separate out each term. So T of x1 e1 plus T of x2 e2 plus T of x3 e3. And then again, because it's a linear combination and x1, x2, and x3 are all scalars, we can pull them out. So it's x1 times T of e1 plus x2 times e of t2 plus x3 times T of e3, which, rewriting this, I have x1 and T of e1 is 1, 2. I have x2 and T of e2 is -1, 1. And x3 and T of e3 is equal to 2, 3. So looking at this, this is multiplying this out. This is x1 minus x2 plus 2x3, 2x1 plus 2x2 plus 3x3. So this is our transform T. And then if we want to go, so actually this is a perfectly acceptable form of writing a formula for T given an X. But we can go further and represent T by a matrix A. Remember, here, what we have is an X times T of 1, X times T of 2, E2, and X times T of E3. So our matrix A would be just these column vectors, 1, 2, -1, 1, and 2, 3. So here is, in general, we can represent our matrix T by using the T of E1, T of E2, and T of E3 as our column vectors for A, which is exactly our next theorem. So if T is a transformation, a linear transformation from Rn to Rm, and E1, E2 up to En are the unit vectors in Rn, if A is the m by n matrix T of E1, T of E2 up to T of En, then T of X, our transformation on a vector X, is equal to the matrix times our vector X. And we have this proof here. So for any vector X, which has components x1, x2 up to xn, that's equal to, because these are just the standard bases, x1 times e1 plus x2 times e2 plus up to xn times en. When we plug this into our transformation, again, very similar to what we did in the last problem, we can then separate out all these terms and do t of x1 e1 plus t of x2 e2 up to t of x and en, and then pull out the scalar coefficients. And so our matrix, if A is equal to this matrix of t of e1, t of e2 up to t of en, then when we multiply it out, we have that our t of x is equal to A times our vector x. An example of this, let's say we have a transform from R2 to R3, and it's defined here. So we take a vector in R2, x1, x2, and we make this, we transform it into the R3 vector x1 plus 2x2 minus x1 plus x2, 2x1 minus x2. We want to find the matrix A such that t of x, this definition here, is equal to A times our vector x. And by this theorem here, A is equal to t of e1, t of e2. So t of e1 is t of 1, 0, and t of e2 is t of 0, 1. So plugging in 1, 0 into our transformation, we get 1, negative 1, 2. And plugging in 0, 1 into our transformation, we get 2, 1, negative 1. So this is our matrix A right here. And you can verify this by multiplying the matrix A times our vector x, and we can see that after we do the matrix multiplication, we get the same as our transformation T. Our last topic will be of null space and range. In our video about dimension, we had talked about null space and range, but just to review, if we let V and W be a subspace and of Rn, and let T be a mapping from V to W, and it's a linear transformation, then the null space of T, denoted null of T, are the vectors V that are in the subspace V, and T of V is equal to 0. So it's the vectors in V that get mapped to 0. That's the null space. The range of T is a subset of W and is equal to the vectors in W such that there's some V in the space V that equals T of V equals W. So it's very similar to our idea of range of general functions. And what we had discussed also in the previous video is that the rank of T, which is the dimension of the range, plus the nullity of T, and the nullity is the dimension of the null space, is equal to n. So this is our example. Let f go from R3 to R2. So here V is in R3, W is R2. And f is specifically defined as x1 minus x2, x2 plus x3. We're going to describe the null space and range of f, sort of a review of what we did in the dimension chapter, but we'll also determine the rank and nullity of f. To get the null space of A, we're going to find the matrix that represents our transform here. And to get the matrix of the transform, we're going to look at what the transform does to a basis vector. And since we're going from R3, we're going to look at what this transform does to 1, 0, 0, 0, 1, 0, and 0, 0, 0. So when we plug in 1, 0, 0 into our transform, we get 1, 0. When we plug in 0, 1, 0, we get negative 1, 1. And we plug in 0, 0, 1, we get 0, 1. So this is our matrix that represents our transform. So to get the null space, we're going to see where this matrix times x is equal to 0, 0. So we solve the augmented matrix, and we get that x is of the form 1, negative 1, 1 times x3. So in other words, 1, negative 1, 1 is a basis for our null space, and the nullity, the dimension of our null space, is equal to 1. And remember, dimension just is equal to the number of vectors in your bases. Rather than going through the calculation of range, which I will do in my next example, I'm going to save myself some work in this example and use this theorem here, that the rank of A is equal to n times the nullity. So in this case, n is equal to, so I'm going to R3, so here's my n, this is m, so R3, which is 3, dimension 3, minus the dimension of my nullity is equal to 2, so that will be equal to my rank. For my next example, I'm going to have my transform from R2 to R3 defined as x1, x2 gets transformed to, or gets mapped to, x1 plus 2x2 minus x1 plus x2, 2x1 minus x2. We're going to describe the null space and the range. Again, I want to represent my transform by a matrix, so by my theorem, I need to see how this transform behaves on a basis, and I'm going to use my standard basis. So t of e1, so if we plug in 1, 0 into this transform, we're going to get 1, negative 1, 2. T of e2, so when we plug in 0, 1 into this transform, we get 2, 1, negative 1. So I want to look at my range of A, which is equal to the y values when I multiply my matrix A times a vector x. So to solve this, to see what the y values look like, so I'm trying to solve for the y values, I'm going to solve my augmented matrix. And then I do my row equivalent matrix row operations, and I get this row equivalent matrix, which tells me that 0 is equal to minus 1/3 y1 plus 5/3 y2 plus y3 here. So solving y3 in terms of y1, y2, that means my range is equal to y1, y2. Those are my free variables. And then y3 is equal to 1/3 y1 minus 5/3 y2. To get a basis for this form of vector, I separate out my y1s and y2s. So for y1, in the first coordinate, I have a coefficient of 1. There's no y1 terms in the second coordinate, so that's 0. And then for my third coordinate, I have a 1/3 y1, so that's my 1/3. For my y2 vector, in the first coordinate, I have no y2, so that's 0. I have 1 y2 for the second coordinate, and my third coordinate is y2 times negative 5/3. So this is my basis for my range. That means the rank equals 2. And again, using this formula here, the nullity is equal to n. In this case, n is equal to 2, minus the rank is 2, is equal to 0. So the null space is equal to just the 0 vector itself. So that's it for the material for this video. We talked about linear transformations and how they were essentially a function that maps a vector to a vector. We said that in particular, a linear transformation follows these two, or upholds these two conditions, that t of u plus v is equal to t of u plus t of v, and t of scalar a times u is equal to a times t of u. And we did many examples of showing that a function or transformation is linear, and also examples of functions that are not linear. We said that linear transformations can be represented by a matrix, and this is the theorem that allowed us to find a matrix. To find a matrix A that represents our transformation, we simply looked at what the transformation did to a basis, and we chose the standard basis. And we showed, and we did several examples where t of x is equal to the matrix A times x. And finally, we talked about null space and range, and we looked at the definition of the nullity, which is the dimension of the null space, and the rank being dimension of the range, and we did examples with this in terms of transformations. For review, I have these 4 problems for you to try, so you can pause the video, give them a try, and on the next slides, I have solutions for you. Actually, on the very next slide, I have a few comments on problem number 3 if you get stuck and you want a few hints. In case you wanted a hint for problem number 3, because we haven't done a problem just like this, but we have done components of it. So first, we're given a basis for R2, and we are told what t does to that basis. So we have done a problem that given a vector, a random vector v, say in R2, we can write v as a linear combination of the basis. And then we can use the fact that t is linear to find t of v. The second component that we've done, that we're going to use in this problem, is this theorem here that tells us how to find the matrix, and we want to know what the transformation does to each of the standard basis vectors. So we're going to use kind of techniques from these 2 examples to do this problem here. This is the solution for the first problem. This is the solution for the first problem, part B. This is the solution for the second problem, done two ways. If you did only one method, you should definitely look and understand the second method as well. This is our solution for problem 3, and the solution for the last problem. And that's it for this video. Thank you for watching.